All right, here's another problem. Oh man, that's not pretty. Oh wait, no, that's fine. That's this line goes a little short. It's not the case that this line goes too long. Anyways, so here's another problem using polynomials to approximate functions. And here we're looking at e to the minus 8x squared. And when you look at e to the minus x squared, we know that that's not a... Is that the one that's not a analytic function, or is it e to the power of x to the power of minus 2? I forget what exactly, but when you see this exponential function here, that should sort of raise a little bit of a red flag, especially when you've got like an exponential mixed with a polynomial in there. Like maybe this isn't going to be such a good approximation. So let's see what happens. We define, so we want to use 5 points equally spaced between -2 and 2. So that means we want -2, -1, 0, 1, 2. And we set our xi values to be those, and then we let I be e to the power of -8 times whatever that xi value is squared. And so we get e to the minus 32, e to the minus 8, 1, e to the minus 8, e to the minus 32. So if we look at what's going to happen, if we look at this polynomial, the ui's here, we're going to start with like so u2 is going to be 1, so that's fine. But for all the other ones, we've got like e to the minus 8, e to the minus 32. All the other terms are not going to have much of an impact on the overall function. So you can sort of see that, like, if you want to get a good approximation, you're going to have to throw in a whole bunch of these terms in order to get a good approximation. And every time you throw in another term, the terms get like super ridiculously small, super ridiculously fast. So it's going to take a very, 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 very lot of work in order to get really good approximations. But anyways, let's take 5 equally spaced points and see what happens. So we're going to want to find a degree 4 polynomial. And we have this formula. And this is a lot like 5.8, where we just find an interpolating polynomial and plot it against the function that we're looking at. And so, but this one is trickier because the computations are a lot more involved, because you've got these terms and you plug in, you get all of this. You have to do this. At least the denominators aren't too bad here. In the previous one, you had pi all over the place, and that was a little tough. But yeah, so you get these, and you do it more, and you collect like terms. You collect the degree 4 terms, degree 3 terms, degree 2 terms, degree 1 terms, and then the final term here is 1, which makes sense because we want the functions to agree at x equals 0, and when you plug in x equals 0, this is going to be e to the 0, which is 1, so it better be 1. But anyway, so yeah, so this is our polynomial, and let's plot it. Yeah, so pretty much like I hinted at, this is not a very good approximation. And so this is also very much zoomed into just the region that we're looking at. And like the further you go out from the region that contains all the points you're using to interpolate, the worse and worse these polynomial approximations get. So basically what I think is going to happen, like because this is a degree 4 polynomial, I think this just looks like a W. And this exponential thing, or I guess, okay, so let's make it like dashed. Then the exponential one is going to just stay flat. So this is not a good approximation at all. But here we actually see a graph, and we can actually, not only do we know theoretically that this polynomial is not going to be a good approximation because we saw that the coefficients of those polynomial terms just get like exponentially smaller, literally exponentially smaller. Not only that, but we can now also see visually that it's definitely not a good approximation at all. And that's going to take a lot of work in order to get a good approximation. But yeah, that's pretty much all there is with this exercise, and yeah, we're done.